Hi, this is circuitvalley.com. I'm Gaurav, and today I'm going to show you what I found really cheap on eBay. This is a PCI card from IBM. I believe it is used in some kind of servers or some kind of POS machines. But what is really interesting about this PCI card is it has a generic FPGA, Altera Cyclone 4 FPGA, and this PCI card you can easily find it on eBay for very cheap. I think I paid 12 euros for it or something like that plus shipping. Right now I can check it is available for around 30 euros and stuff like that. This PCI card, if you want to find yourself, it is 98Y2610. If you Google this part number, you can easily find multiple listing of this particular PCI card. Why we are talking about this little PCI card is because if you want to do experiments with PCI on an FPGA, you need to pay a lot of money for a PCI card, and this particular unit is available only for 12 euros. So you can easily get your hands dirty with PCI experiments using this PCI card. It happened to be an Intel Altera Cyclone 4 part. I would have preferred if it would be Xilinx or something like that, but Intel FPGAs are also okay. So you can see in front of you there are at least 4 power supplies. There's some kind of MOSFET from IRQ, and in the middle I believe this is a WinBond chip, so this is most likely going to be the speicher, the configuration memory for this chip. And this particular card on the back, let me flip it. On the back it has these two RS485 power ports. These are not Ethernet, they are RS485 ports, and you can find some information about this card, but mostly it's listed IBM RS485 card. And if you really want to locate it quickly, this part number will help a lot. There are multiple LEDs there. So once you power this card, these LEDs may return some status. We will power it on. I have not yet tried it. So together we will try to reverse engineer this card. And as I have told you, this is a configuration memory. As you can see, it's a little bit marked red there. It may be denoting that it's being programmed. Okay, and there are two RS485 transceivers. There are 4 primary chips in the front end. You can see, I believe this is the part from Linear Technologies. As you can see, the logo, its part number is 1686, and if you Google the part number, then you will find it to be LTC 1686. It is RS485 transceiver. Same part is again there, 1686 RS485 transceiver, and these parts I believe from Intercell ICL3221. These are RS232 transceiver, both of them. So on these ports you have at least RS485 and RS232 available, and there are multiple LEDs. There is some unpopulated connector or something like that. It doesn't appear to be an IC. It appears to be some kind of connector. This appears to be unpopulated IC, but if you look at closely, this appears to be the footprint, and everything else quite matches with this Intercell IC. I don't know why it's unpopulated. We will find out soon. We will completely reverse engineer this board and try to find out which exact pin connects to which pin, and we will try to match we'll try to get the firmware up and running. We'll try to get flash our custom firmware there and get our own PCI link up and try to operate maybe these LEDs if they are directly connected to the FPGA, or maybe try to send and receive data over RS485 or RS232. It appears to be that there are at least 2 connectors, one here, one there. Either this is the JTAG connector or this is the JTAG connector, because this is the IC. One of them is going to be JTAG connector. We will find out soon which one it is, and we will try to reprogram this FPGA, and we will find out if we can use it for our own experiments. On the back side of the FPGA board, there is not much going on. There is just few passives everywhere. So I assume there's also a fuse, and I assume that one of these connectors, this connector which is unpopulated or this connector which is unpopulated, one of these connectors is a JTAG connector. And we will see through experiments and through elimination and through logic that we will try to reverse engineer this board and try to find schematic of this. If you want to take a little bit closer look, let me zoom in a bit. Now it's in focus. Again, Intel FPGA, some kind of MOSFET, configuration memory for the FPGA, 2 RS485 receivers and 2 RS232 receivers, and these are the appears to be power supply. We'll verify if everything is working. This appears to be a capacitor on the power input. So in theory, we can, if you do not have a PCI connector or PCI power supply available, we can just use this capacitor as a primary power input, or maybe we can probe somewhere here and find out which is the primary power input, and we will try to supply in 12 volts. And I hope that these regulators will regulate down to some other kind of voltages, and which is more useful for the FPGA. And you can see it says, one funny thing is there, it says made in USA, and on the back side it says made in China. So I believe the PCB may be made in USA and the board may be assembled in China or something like that, but it doesn't matter. We have a nice little FPGA from Intel. I'll go to my computer and I'll show you what part it is, trying to find the data sheet of the part, and we will try to find the pin out of the part, and we will see how does it match. So this is our part EP4CGX22BF15, and we need the pin information of it. Maybe we need to search for Cyclone pin information rather than this part. Yeah, so something like that will do. And problem with this kind of pin information is this little bit structured in a different way, and I do not know which exact part we have, which VGA part number it is. And let me take a look. It's BGA 169. So these are our pins, and you can see this part has these transceivers, and it has at least one RX, one more TX, one RX, one more TX. Okay, so it has at least two pairs of RX and TX, total 4 high-speed transceivers. So in theory you can do PCIe X2 with it. The board which we have right now, it's only PCIe X1. So, and rest of the pins are also listed for BGA 196 for this FPGA 169. I have figured out that it is better to use a PCB program and route according to that. So I have opened my PCB program and I will go and look at the part number there. I already have Intel library, and we will take a look at the PCB program, how it helps, because this kind of pin information, it's helpful, but it's not that helpful to do PCB reverse engineering kind of stuff. And let's go to the PCB program and we will look for our correct part, and we will see there. So I'm in my PCB program and I have created one project, and it's called Cyclone PCI. There's also library included for Cyclone 4. And let's go to the schematic library. This library is available on internet. So let's look at which part we have. We have any of these parts. EP4CGX22BF14. I do not really know what the C4, C7, C8 means. Most likely this is like speed grade. If you look on the right side, this is speed grade only. So this is C6, CZ. It doesn't matter for us because speed grade doesn't change part. So I have already taken this part and already laid out everything. So you can see on your board there are 6 banks total, and these are the normal IOs, and this is I believe this is the clock bank or differential clocks, and these are the 2 references clock. I believe these will belong to the PCI. So, and this is the PCI block. So you will see these are the transceivers, RX and TX, one transceiver pair, second transceiver pair, and one of the clocks may be associated to one pair, another clock will be associated to another pair. That's my assumption. Is this is our JTAG, and we're supposed to debug this JTAG, and as you can see there are not that many pins. So most likely our this header which we saw, this low density header or this unpopulated footprint, that's going to be our JTAG. And these are power supplies. Power supply matters at this moment, but not that much. I assume that power is going to be connected to 1.8, 3.3 or some other voltages. It is not important for us. Primary thing which we are interested in, which PCI is getting used and which pin connects to where and which clock is used and stuff like that. So you can see this J1 and J2 and G1 and G2. And let's go to the PCB. I'm in the PCB view, and you can see this is the pin number 1, and if I match with my board, pin number 1 is so on the board pin number 1 is on this side, and you can see these pins are routing and they may be terminating somewhere here. I'm pretty sure they are not going to go through the package or go all the way through. They will definitely terminate there. And you can see this is a pair. This is the one PCIe lane, because this is a PCI data pair, not really clock, because clock is on the PCI on the back side. Let's flip the board and show you the clock. So this is the clock, and this is another pair, and the clock goes like this and it connects in the middle, and the data pair also goes up to here and terminates right there. So most likely our PCI is terminated there and clock is going somewhere in the middle. We'll try to figure it out, how does it goes. Let's flip the board one more time. Let's go back to the PCB program and we will try to map which exact PCI pair is being used. So now I'm at the PCB program and I have flipped it so that my pin number 1 is oriented downwards, and if I go back to the schematic, you can see J1, J2, G1, G2, E1, E2, C1, C2. These are the pins, and we remember that our pins, PCI pins, were coming from the bottom and they were terminating somewhere here. So J1, J2, E1, E2, and G1, G2 and C1, C2. G1, G2 and C1, C2. So this pin, this pin, this pin, this pin. These are your PCI pins, and clock is somewhere in the middle. We don't care about it right now. So let's find out which exact pin it is. We will use our multimeter and we will try to probe and check just for continuity, because the VRs are available for probing, and let's find out. So I have my multimeter in continuity mode. These are some handmade probes. I use very thin probes so that I can reach out very small places. So let's see. So I can already judge by just the orientation of it that this one is going to J1 and J2, but we will still verify. J1 is the 5th number pin on this, from this side, 5th number pin. Okay, let's flip it. Okay, and when it goes to J1 and G2, you can judge by schematic. Its another pair should be going G1 and G2. So we'll, for the sake of verification, because otherwise that probing is difficult. So when the pair is going to J1 and J2, the other pair is going to J1 and J2. The pair on the back side is going J1 and J2. So this one should be going G1 and G2. So we'll try to probe if it is going on G1 and G2. And G1 and G2 is we can use our multimeter to find out which pins they are going to. But in this case, I think in the PCI case, this is quite obvious. This is going from here and going only way up to here. So we can quite easily judge which pair it is. For the TX side, maybe we need to exactly know which one it is. We'll use multimeter there. But if you're able to find out where this pin is going, so other pin is definitely going to be the opposite side. So if it is connected to PCI 0, the other one is definitely getting connected to PCI 0 other pair. For example, this is TX, the other going to be RX, and it's going to be opposite pair. So if it is, most likely it is in the center of the part, so it is going on G2 and G1, and the other pair is going on C1 and C2. Okay, and now we need to find out which exact clock pin is going to. Most likely is going to be the reference clock number 0. And the pin, I can tell you our PCI, this is connected to G1 and G2. This is connected to J1 and J2. And on the back side, this is connected to J6 and J7 right here, the clock pins. So we got PCI figured it out, and we will use some other program. I'll show a program which is written by Alex Posh, the developer of this Ethernet, a well-known Ethernet stack on internet, and we'll use his program to flash a firmware, and that firmware will output on every single pin a UART signal, and we will use our oscilloscope to find out which exact signal from this side goes to which pin and stuff like that. But before that, we need to figure out JTAG. So JTAG, you will need to find out where the exact JTAG pin is going, and we will probe here. Most likely this is going to be JTAG, and we'll probe and find out which exact pin is exact pin. And most likely this connector is going to be JTAG, and we will put our multimeter here and put on the back side. It has to be on the back side because the balls are only exposed on the back side through these vias, and we will put our multimeter on a via, specific via, and try to find out which pin is exact which pin. So we'll mark, this is our PCI RX and TX, and this is PCI TX, and clock, as we have proven, it's going on J6 and J7. So this is ref PCI clock. Okay, so we got two pins figured out, and now we need to specifically focus on JTAG. So we'll look for A3. Okay, and let me show you where the A3 is. So this is A3, the third number pin from the bottom and the first one from the left. So let's go back to the PCB, and we will first try to find TDI. Okay, which pin it is. I will go and probe on the connector. It's a little bit hard and tricky to do, but we can hold it, and I'll go on the bottom side and find out where it beeps, if it at all beeps somewhere. I'll try both of the connectors actually. I do not get a continuity anywhere at all. Maybe it's because of the conformal coating. I tried this connector, whole connector, and this as well. I have no idea now. I have tried this connector and this connector both, and it didn't work. Let me zoom out a bit. You don't need to focus on this much. Okay, so let's try. Maybe I hold it like this. This is hard to do on camera, but you have to try it for the sake of your enjoyment. You have to be really careful not to put too much pressure, because it will damage the PCB if you put too much force there. Okay. Yeah, you can put a force because it's primarily solder. Still no nothing. And let's find out here. Maybe we go here because there is no flux or residue there. No, there is absolutely no continuity anywhere at all. It's not shorted to ground. Maybe I'll try to probe one more time on the back. And I'm literally probing the third number one more time. Same stuff. No, nowhere at all. Does it even on? The multimeter works, and I'm probing the third number is correct. So, no luck. I think we need to wait a second. A3 on this side. A3 is on this side, not on that side. So this is third number via. Okay, and now let's try one more time. So we found A3. So this 1, 2, 3, 4, 5, 6, 7, 8 pin connector, and third pin is TDI. So we did find one pin. So this, as I suspected, this is the JTAG. I don't know which connector it is. We'll find out soon. So this is JTAG and this is the TDI pin. So we don't have to probe that big connector. So we'll try next pin, TDI. We found out pin number 3 on that big connector on this side. I don't know which side is, I don't know which. Oh, I cannot tell you if this is pin number 1 or this is pin number 1, but it doesn't matter. This for us, this is pin number 1. Number 3 is TDI. So I have already created this 10 pin header. We will just use this 10 pin header as a TDI or as a JTAG connector for our orientation, for the sake of completeness of the schematic. Let's do it. So pin number 3 was TDI. So TDO is A1, and A1 means this pin, this exactly in the corner, and we'll find out where this TDO is lying on the stacker. Let's do it. So I have connected to VIA. Let me put it on your focus a little bit. I'm not that bit good at videography. Third, you no need to probe because you already know it's TDI, but still I probed it. Maybe I was not making good contact there. Again, I'm doing something wrong. Did I damaged it or what? Yeah, this is the problem of doing stuff on camera. You can see I damaged the VR a little bit. It will still work, but there's still damage. So I was not supposed to do it on camera, but for the sake of everybody finding out, let's do it still. This is not also it. So this is our TDI pin. Okay, so this is the pin, TDO pin, sorry. This is the TDO because we saw the continuity there. This is the TDO because we saw the continuity there. Let's make a note. So we have found the TDO as well. Let's go to the next pin. B3 is right next to A3. Let's go back. So this is A row. As you already know, this is the A row, and this is third number, so this is B3. I'll hold it gently this time. It's supposed to be maybe the next pin or this pin. This pin, last pin, the 8th number pin is TCK. So we find out the TCK as well, and now let's go to the next pin. So A2 is going to be the next pin, and you already know this little damaged or scratched V I have right next to that is A2. Now I have it on grip. Let's look how does it look there. So this is TMS. So 1, 2, 3, 4, 5, 6. 6 number pin is TMS. So we figured out all the 4 active signals. 2 are here and 2 are here, and there's going to be ground somewhere. Let's figure out the ground as well. Maybe we'll take this pin as a ground. This is definitely ground, and let's see where is the ground. This is definitely not. Okay, so we hit the jackpot on the first try. This is the ground, and this is definitely not ground. This is the ground, so pin number 7 is ground. So we got three more pins to figure out. Most likely two pins are going to be empty. This appears to be connected somewhere. They're going to vias. I don't know where they are going. Or this is also connected. These are the 3 pins which we didn't figure out, and this, and this. So one of them is going to be most likely a reference voltage for the programmer, and 2 I do not really know what they're going to be, but it doesn't matter. We needed primarily clock, TDO, TDI, TMS, and the ground, and we will need the reference voltage as well. So I'll next solder. So next I'll try to figure out where is the power supply input. These are the power supply 12 volt pins, and where they're going. Yeah, so I doubted, my doubt was correct. This is the primary input capacitor. So we'll solder 2 wires right here, and try to feed in 12 volts, and so that we can power the board and see what does board behaves and where our reference voltage for the programmer comes. Let's do it. So wires I have soldered, and Let's connect the power supply as we have figured it out. Actually now forgot which side is ground. This is ground. Yeah, so this side is ground and this is definitely power supply. PCI is normally 12 volts. So I'll connect it and will power it through my bench power supply. Third channel of the power supply is connected to my board. Let me turn it on. It consumes around 125 milliampere, but doesn't do anything. Most likely, to be able to do anything at all, it will definitely need power. It will definitely need a PCI link. Okay, so not to worry. And our primary goal is to figure out the JTAG pins, and where is the JTAG reference voltage is coming in. As you can remember, we figured out that these two pins are TDI, TDO, and there's a clock and TMS or something like that, and there's a ground. So this pin and these two pins, these are the pins which are remaining, and we will try to measure them. Now I have to switch to voltage because circuit is active. So let's see, I'll take ground from there because it's basically similar thing and basically same thing. Let's measure this voltage. Let's measure 2.5 volts, 2.46 volts, and this measures 0. And this measures also 0. So I'm pretty sure this is our reference. This is 2.5 volt reference. So we have 2.5 volt reference, TDI, TDO, I don't know which one it is, and TMS, clock and ground. And these two pins either unused or they are routed to the FPGA or somewhere, or maybe routed to the bin-borne chip for some purpose. I have no idea right now, but it doesn't matter. We figured out. We will solder a header there. Header looks something like this. I have already broken it into pieces, and you can see this is both ways, and it is 8 pins, and we'll solder it like that. So I have soldered the header. The flux is not yet cleaned, but this should do. I have already made a cable which will fit. This red represents reference voltage, and this cable has another side connector, IDC connector. We'll be using this guy to program because I do not have an Intel programmer. And this is a bus blaster from Dangerous Prototype. I use it for quite a few things. It can do JTAG directly, and we'll try to program it, and this thing get plugged right into there. Most likely it'll plug like this. Let me see, BTGT, because you have cut the notch, so it'll plug like that because I do not have the appropriate connector for it. So this will do as a hack, and we will plug it in and we'll see if this gets detected by the JTAG or not. We'll power this board, we'll plug the USB. Board is connected to bus blaster and powered from my bench power supply, currently consuming around 128 milliampere at 12 volts. And let's go to my computer and we will try to get the JTAG connection, and we will see how we can use this bus blaster to program Intel FPGA. In the case of this programming, we will use EUR JTAG, and we will try to detect this as a JTAG device, and we will try to use BSTL file to have the configuration, and we will use SVF file to program this thing. Let's go to my computer. So I got my EUR JTAG running, and we will first need to detect a cable. So cable FT2232 and PID is equal to 0x6010. VID is going to be 0x0403, and interface supposed to be going to be 0 to detect targets for the bus blaster. Cable is detected, and we say detect. Okay, so this is the FPGA which is got detected. I am almost certain because this is the FPGA for us, and if you want, we can verify as well if this is the device, but I have a better way. I already got the BSDL file set up, and BSDL is BS is live on my C directory. So BSDL path is set. Let's do the detect one more time. Okay, so it has found the file named is like that. BSDL file can be downloaded from FPGA manufacturer, and this I downloaded from Intel's website. And if you go and open this BSDL file, you will find this manufacturer ID somewhere, and device ID somewhere else, something like that. So it's going to be Altera and it's going to be part number. And this is, I'll show you. Let's go open the BSDL file. So this is how a BSDL file looks in Notepad++. This is the part number, this is the version 1.0. I believe there is 1.2 also available from Altera. And the IDs which we were talking about, there must be somewhere here. Let me see. Yeah, so this is it. This is all 32-bit programmable ID, and this is 11-bit manufacturer ID, 16-bit part number ID, and some version information which I don't understand. And this is how it looks. Let's go back to the EUR JTAG and we will try to program a SVF file. So as you can see, this device and everything is detected. Now we need a SVF file, and this SVF file need to be generated from the Intel software, from the bitstream file, and for that we need a project. As I have suggested, there is a project from Alex Frost is available about the reverse engineering of the FPGA, and what that particular project does is it initiates multiple UART modules, and every single UART module will be outputting the pin number of that particular pin. So we will go with the oscilloscope and we'll try to probe every single pin, and we'll find out exact pin number, exact ball number where it is, everything is connected. So I'll open the Intel's software now, and then we will try to make a project and compile a binary. Now that we have cable detected and the part is also detected and BSDL is also detected, now we can do SVF, C, $UART.svf and stop and progress. Okay, it's done now. We'll go back to the board and I'll show you how does it look on the board. So if you have really keen eyes, you can see these LEDs, all of them are lighting up a bit. Let me turn off my studio lights and we'll see how. You can see they are all lit up because they are all transmitting UART signals. Most likely you will see UART coming here, everywhere there will be a UART coming. So I'll try to use my oscilloscope and oscilloscope's UART decode function. So I'll show you probe for a particular pin. Let's turn on the lights and turn the brightness a bit. So I'll be using my RTB2004. Let's try to have ground from somewhere. We will take the chassis ground. It's somewhat hard to probe with everything hanging in the air. So let's probe this pin. I assume this side or that side, we will see a signal. So I will see this side and let's see this side. I see a signal on the oscilloscope and I'll show you now with the camera. I'll leave the probe from there. You see a UART signal. I assume it's a UART signal, and now you see it properly. Let's do a single capture. Here it's some kind of UART, and let's first. I did not pay all that much attention setting up this UART. So first of all, we need to find out the baud rate. Baud rate is easy. So you have to find the shortest pulse. I assume this is the shortest pulse where we triggered. I'll get my cursor and just set up the cursor there. This oscilloscope has really nice interface, has few bugs, but it's okay. So you can see the delta around 1 megabaud per second. So delta is around 1 megabaud. So let me, for the accurate reading, it is around 1 megabaud. So let's set up a UART protocol decode on UART configuration, and right now it's set to 1150 1 mega. Okay, so we'll do one more single capture. Maybe we need to set the UART decodation and its display appropriately. Display setup, we will display ASCII characters. Should be showing the ASCII characters. or something isn't right. I think it cannot decode for some reason. Okay, that's one problem. I'm pretty sure I did not send any parity and did not send. Let's do one more single capture. Yeah, now we see it. Yeah, sorry. So now we see it, and that I transmitted C13 on this line, and now I can maybe trigger it better. I'll do a H, or maybe not a pulse trigger, and we'll see pulse greater than around 2 of time divisions, greater than 2 microseconds of positive going pulse. Sorry, 20 microseconds, 20 micro. Now we'll see, I should see a better trigger. So now trigger is set up appropriately, and you're looking at the better trigger, and it says this is the pin number C13. Okay, and I'll show you other LEDs. This is pin number B13. This is pin number A7, and another LED pin number A13. So I'm probing one LED after another. This pin C13, so B13, and next pin A7. Let's probe this connector. Let's see if there is a signal coming there. There should be a signal coming there, I believe. So I see C6, B6, and next signal there is no A7. Something like that. So you're supposed to probe out all the pins, and then you will have a schematic, and I will do that work offline, not on video, and I'll show you the final schematic. Just another tip, most of the modern FPGAs nowadays, they have their own clock generator, on-chip clock generator. So you're not supposed to supply any clocks. If you do not know which pin the clock input is coming, it is not really necessary to know. As you see, this is an internal oscillator, and I'm just using this clock output to generate my UART. I did not pay any attention to which baud rate it is, because I can measure the baud rate on the oscilloscope and set my baud rate accordingly. So now that we have a shell plan, I'll show you the schematic. So with the same method, I have populated whole schematic, and you can see LED 9 and this and that. Everything is populated. RX 485, ICL, Intersil TX invalid, and power good, PCI reset, red LED left and right, PCI reference pin, 100 MHz input. This board also have one oscillator going to H13. It's not necessary to find out its pin out for reverse engineering, but I have figured out that some of the pins which I could not able to figure out, or they are not connected to anywhere on the board. These are the pins. So we'll try to now. So we are done with the reverse engineering, and we have the schematic of the board. And this board is not very complicated, so you don't need much efforts. But still, for 12 euros, which I paid for it, plus 3-4 euro shipping, it's a really nice, wonderful board. The only concern I have with this board is that it has an Intel FPGA and tool chains of Intel FPGA, primarily this Quartus and everything else, very easily available, and documentation is also very, very lacking. For this particular board, every source, and I have also found some PCI project example, is available on my GitHub. You can visit my GitHub there. And I have also available this UART projects and schematic. So you can, if you have similar board, you can just use the schematic and enjoy yourself Intel PCI, if you can enjoy it. So that's it for this video. You can visit my website www.circuitvalley.com.